So so we need to modify some compilation script in the spec benchmark. So I tested some compilation of these benchmarks using Docker images. So I tested these compiled binaries to to I also ran these compiled binaries in Gen5, and then it worked fine. Okay, so actually, so you need change the baseline configuration for the spec 2017 compilation. So actually, we will use the this 0 optimization level. So it's actually not optimization. And then you need to change this architectural custom x86 64. So this is a native 64-bit x86 ISA. Also, you need to set the static option for the GCC. Okay. Then you can run the compiled benchmarks using Gen5. So actually in the first the first assignment, I selected 10 benchmarks from spec 2017, but I found that the last two applications do not work using Gen5. So we will test these nine applications. So I include the Spectre POC, the proof of concept. So you can run these nine applications using Gen5. Okay. So I describe how to generate the binary files for running Gen5. Also, in order to run these binary files, so you need to also require data set used by applications. So you need to also copy the data sets to your host machine. Okay, and then in order to run the binary files using data sets, then we need to set up command and then the execution options for the benchmarks. So you can also extract these options using the spec utility. So you can change this command part and the option part, the Gen5 command. Okay, and then for this simulation, we will use the Gen5's system code emulation mode. So the system code emulation mode, Gen5 just executes the binary file, compiled binary files, and then so there is no influences from operating system, or so there are no influences from the other I/O devices. This is just a very simple binary execution mode. So, but if we use the full system mode, then we require some storage systems. So we also require the operating system to run the Gen5. So for this assignment, we will use the system code emulation modules, and then we will use the provided example configuration. So let's say the pi to run the Gen5. And actually, you can set some different system configuration, which that is great. Okay, so as you can see, we can set the size of the cache. So we can also set some associated of the different cache configuration. So actually, also we can compute the different configuration for the memory. So processor type, CPUs. So in this default processor models, and we can compute the different system model. Okay, so this is the some example execution command for Gen 5. So you can find this command. So it's a binary file. So you can find so actually this is Spectral POC does not require any options. So you can for normal spec benchmarks require so data sets or execution options. So you need to also set some options for executing the binary files. And then, as you can see, you can set the various CPU types like here. So then we can change the memory size and then the cache size like this. So, and then you will be requested to run 100 million, like 100 million instructions using Gen 5. So usually for the 100 million instructions, it took about 10 or less than 10 minutes or 10 or 15 minutes. I didn't so. 얘가 뭔가 지가 알아서 하는 거 같아. So it will take 10 or 15 minutes for each application. Okay, so actually I recommend you to start this assignment as early as possible because it will take time. Also, if you run this bench, actually I set the number of threads, so you need to set the number of threads for the spec compilation as 1. So which means that the Gen 5 will run on the 1 thread. So which means that if you have multiple cores on your machine, then you can launch Gen 5 many times, and then so you can exploit the multiple cores on your machine. So which means that you can run multiple binaries using Gen 5. So I recommend to use the Docker image for running Gen 5. So which means actually if you use the Docker image, then you can set the same environment, same execution environment for the for running architectural simulator. Also, if you use the Docker image, then you can use the same image file, and then you can run the multiple containers using the Docker images. So which means that you can exploit the multiple cores on your machine. Okay, so some tip. So actually, so it's important for your career actually. So if you use your machine effectively, then you can reduce some working time. It's good for your career. So it's very actually important, okay, for your career. But actually, kindly, I provide the Gen 5 command generation script. So this is the example script, and then so in this script, then so this is the bash script. Okay, it's not Python, it's a bash script. So in this script, then you can set the benchmark name, also the benchmark directory. So you can set the benchmark command and the options. And then based on also you can set the processor configuration using this script. So actually, I tried this best forward option because initially the cache memories are empty in Gen 5, but if I activate this best forward option, the Gen 5 encounters segmentation fault, and I did not cite this issue. So do not use the best forward. So as you can see, when the Gen 5 command is generated, it uses only the max instructions. That's the maximum number of instructions. And then unit sector is maximum number of instruction as 100 million. Okay, 1번이에요. Then this script will generate the command.sh, which is also the shell script. And then if you execute this command.sh under the benchmark directory, then you can run Gem5. So, and then not check the result from the Gem5, then you need to check the stats.txt. So this file includes some performance metrics generated by Gem5. And then you can find this stats.txt file under the which directory? Gem5 result directory here. So you can set also the Gem5 result directory here. Okay. So actually, using script is also very good for your work practice. So if you utilize some script languages, then you can generate a very effective script. Then you can reduce some working time in the computer. Actually, it's also very important skills for your research or for your career. Okay. So for this assignment, so I explained how to run the compiled benchmarks using Gem5. So please read through this document, and then please follow some instructions on this document. Okay. So and then for this assignment, you need to analyze the characteristics of very popular workflow. Okay. And then in order to analyze the characteristics of workflow, then we can test some sensitivity of the benchmarks or workload. So in order to check the sensitivities of workload, and we can change some configurations of the system on the processor. So for example, if we want to check the cache sensitivity of the workload, then we can change the cache size, like the 8 kilobyte, 16 kilobyte, 32 kilobyte, and so on. So by changing the size of the cache, then we can also measure the changes of performance, like the IPC, or we can measure the CPI. So, but usually, but IPC is proportional to the performance of the processor. So we can measure the IPC by various size of cache. And we can analyze the cache sensitivity of workload. Okay. So in this assignment, so actually you need to run the compiled binaries many times using different configurations. Okay, so you need to change the add-on cache, add-on instruction cache, like how many times? 5 different configurations. Also, you need to change the add-on data cache, size of the add-on data cache for some 5 different sizes, 5 different configurations. So you need to check the add cache, you need to check the branch variable. So finally, the question is to compare some specific characteristics of a specific application, such as the Spectre. So Spectre is the kind of speculative transient attacks. So this is security attacks that exploits the architectural vulnerability on processor. So you can also compare some performance metrics from Gem5 or the normal benchmarks, such as the spec benchmarks and the Spectre POC. So it's a security attack. So you can also compare the, you can find the specific performance metrics or specific characteristics of the spectral POC, then you can detect some security attacks such as very similar, which is similar to spectral attacks. Okay, so this is the brief explanation about the last assignment. Okay, so any questions? So I recommend you to start early as possible, because as I mentioned, not run this binary benchmarks, then it will take about 10 or 15 minutes per benchmark. Okay, so then for this assignment, you need to try different configurations, such as the different Ln I cache size, Ln D cache size, H cache size, or branch predictors. Okay, so it's that. So it will take long time. Okay, so if you can use the script, so actually I usually use the bash script to run this architectural simulator. So we can use some scripts to extract the performance metrics from the result from it. Okay, so if you can use the script for running the multiple containers, so like the Docker containers, so then it will be very convenient, and you can run the script, and then you can select, and then you can check the result after some time. Okay, so any questions? Okay. So in the previous class, I introduced some GPU architecture. So actually, I introduced about the GPU. I briefly introduced the GPU memory systems. So if you see the execution units in the GPU architecture, and you can find that there are many CUDA cores, it's a simple cores for the integer or floating point operations. Also, you can find the load store unit. Also, you can find the special function unit. Also, in the recent GPU architecture also includes the tensor cores. So tensor cores just to execute the matrix instructions, matrix related instructions. But so in this time, so we will focus on the structure architecture of GPU load store unit. So actually, the performance, we already know that the performance of the memory system is very critical for the performance of the processor. So actually, it is because the processor fetches the data from the main memory, and then this data should be moved to the register file of the processor, and then the processor just read the data from register file and execute the instructions using this data. So the performance of the memory system decides the data movement time, what data movement cost inside the processor, and then it's the same to the GPU. So GPU also has the load store unit, and then the problem of the GPU is that the GPU runs the large number of concurrent threads. Okay, so I mentioned that the GPUs can run the 100 or 1,000 threads concurrently, and the problem is that if the 100 or 1,000 thread execute the memory-related instructions, then it will consume the other resources in memory GPU memory subsystem. Okay, so, and it's not good for the performance of the GPU. And then it's the same to the CPU actually. If you use the multi-core architecture, like CMP, chip multiprocessors, and then the problem is that the performance of the memory system influences the performance of the entire processor critically. And then also some memory transactions from the other thread also influences the performance of the another thread which is running on the different core. So it's the same the multi-core architecture. Then think about the GPU. The CPU can run the hundred of thread. And then if the hundred of thread access the memory systems concurrently, and what will happen? So it's a very severe problem of the chip actually, parallel processor architecture. Okay, and then for GPU exploit the memory coalescing to solve this issue, and then I already explained. So memory coalescing is that. So I already explained that GPU's SM, the streamer multiprocessor, use a warp. Warp is the group of tangent thread, and then usually the warp size is the 32. So which means that GPU groups 32 thread into warp, and then GPU just execute this warp. Okay, and then using this warp architecture, GPUs can utilize the tangible simple cores in the GPU streaming multiprocessor, like the Cindy machine. But the problem is that, so the memory system like cache has the only 2 ports, like the one port for the read operation, and another port is for write operation. So I think I already explained, but so when the memory transactions are generated from this storage thread, then we can generate the maximum storage memory transactions. And then if these storage memory transactions access the cache, and then this access should be serialized because the cache has the limited resource like the port. So the cache can only handle the 1 request per cycle. So and then if the 32 transactions are requested to the cache, then it will take the and miss 32 cycles. Okay. So if the miss, then the cache need to handle the this behavior for these transactions. Okay, so it's very important. It's very important to reduce the number of transactions from warp. Okay, so I will show that this loop line diagram of the GPU, and then that this loop line diagram shows the performance by the memory coalescing. So if we see this performance, so we already know that so in the loop line diagram, so this slope is determined by memory bandwidth. Okay, and then this horizontal line here is determined by computation performance. So if you see that this slope, then you can find that with the various level of coalescing, the performance can be improved. So which means that if we use the full coalescing capability, then this is the performance of some prime performance for GPU. So compared to this line, we can know that the performance can be improved by memory quality. So it's very important to reduce the number of transactions. So I already explained the memory quality. I mentioned the memory coalescing. So memory coalescing means that with the memory coalescing, GPUs merge the multiple memory transactions into a single transaction. So how? GPUs also use the cache that has large block. So usually the CPUs use the 32-byte or 60-byte cache line size, but GPUs use the 128-byte of cache block. So which means that the cache block size is larger than the CPU. So why? Why 128 byte? The size of the cache block is influenced by the memory, the main memory transactions. Also, it can be influenced by how the threads are executed in a processor. So the size of the one cache line is also determined by burst length in the main memory. It's very critical. Also, the GPU, GPUs access the GPU execute the warp, okay, and then warp includes the 32 thread, and then as you can see, as I mentioned in the GPU execution model here is the user prompt. So GPU just convert this iteration loop as the parallel executions. Okay, so execution means that GPU just handle the instructions of GPU just handle the array data, and then the element of the array data is accessed by indexes. Okay, and then when the warp is organized, neighbor thread. So neighbor thread means that whose thread indexes has the similar values, similar indexes. So indexes of these threads are determined by some dimension of a thread in CTA corporate thread block, and then when the warp is generated, actually neighbor threads are grouped into the same warp, which is obvious actually. So which means that the thread index X is the 0, and the thread index for X is the 0 for this thread, and the thread index for this thread is the X is 1, and the 2, 3, and something like that. 1, 0, 1, 2, 3. So thread index is incremented by 1 for the neighbor warp. So which means each thread usually access the array element, and then when this iteration loop is executed, and then actually we already know that the very next iteration loop access the neighbor elements of the array, right? And then it was the same to the GPU. Neighbor thread, so adjacent thread just access the adjacent elements in an array. What does that mean? Usually, GPU's warp is in the strong spatial locality. Okay, which means that the GPU's cache block size is very large, so 128 byte, and then each thread each thread may access the adjacent element in array, like array number 0, array number 1, 2, 3, blah, blah, blah. So you can merge it. Transaction from multiple thread. If this transaction can be merged into one cache line size. Okay. So which means that if the element size of a certain array is the 4 byte, okay, and then a warp includes the 32 thread, and 32 multiplied 4 equals 128. So which means that the best case is the best case. The best case, one warp, the memory transactions from one warp can be included in the one cache block of the GPU cache. So 128 bytes. So it means that we can, from these 32 independent transactions, we can, with the memory coalescing, we can generate only one memory transaction. So the number of transactions are reduced to just one. It's the best case, actually. And then, and then I also mentioned that GPUs are originally designed for graphics applications. And then, the multimedia applications just handles the very regular type data. So actually, it's a matrix is very dense, and then the multimedia application just use the elements in the matrix, very large matrix. So it's a very dense matrix. So if we can, if we just apply the memory coalescing, then GPUs can effectively reduce the number of memory transactions from a warp. Okay. Here. So, and then I mentioned that this is the best case. So, it means that if these multiple memory transactions can be merged into a single transaction, it's the best case. But sometimes these requests are divergent. So this is another example of the memory transaction from a warp. So in this example, this thread just accesses this data, and then neighbor thread. Even though this thread is the neighbor thread, this neighbor thread just accesses the different data. And then, in this example, if we can say that this is the one cache line, the GPU cache line, but this thread accesses the data in different cache block. Okay, so this thread accesses the different cache block. It is possible because GPU use the SIMT model, and then so actually in a program, to the programmer side, it looks like that each thread run individually in a GPU. It's a kind of illusion. It's an illusion, but this is the programming model of the GPU. So, and then also this is some specific characteristics of SIMT architecture. It's different from the SIMD. So in the SIMT architecture, we can think like the multiple threads can be executed individually. Okay? But in the SIMD architecture, with a single instruction, the multiple data should be used for single operation of the single instruction. But with the SIMT, you can think that these threads can be executed individually. Okay, it's kind of illusion actually. So actually you can think like that. GPU supports the SIMT architecture. SIMT programming model, but inside of the GPU is designed like a SIMD. Okay, so it's a kind of a wrapper of the SIMT. So this type of memory accesses are also possible in the GPU architecture, but what are the disadvantages of this type of architecture? For one, will generate many memory transactions, and then if the coalescing is not effectively performed in the GPU architecture, and we already know that GPU performance can be degraded. Okay. So this is the impact of the GPU memory coalescing. And actually, GPU try to increase the performance using memory coalescing to reduce the number of memory transactions to some GPU memory subsystem. But some applications exhibit the very diverse memory access patterns. That it's not good for the GPU performance. So actually, we already know that GPUs are good for the parallel execution or parallel applications. So many researchers or many companies try to use the high performance GPU to run the machine learning or neural network applications. So, but GPUs can be used for other types of applications. That's why GPUs, recently, GPUs are called the general purpose GPU. But which means that general purpose applications, sometimes some type of general purpose applications exhibit the uncoalesced memory test. So it's a very diverse memory access patterns. So, but GPU, in order to increase the performance of the GPU, then if the memory access patterns are converged, so which means that if the multiple memory transactions can be merged in the single memory transaction, it's good for the performance of the GPU. But it's not so like the general purpose applications that exhibit the very diverse memory access patterns. These are called the irregular memory access patterns. So it's not good for GPU execution. Okay. So it's also kind of very important research topics in GPU architecture. So how can we support the irregular memory access patterns some general observed in the some other general purpose applications? Okay. And then loop-like model. So loop-like model is a very popular performance model for the processor popular systems. So, and then loop-like model just to show the potential performance of the processor. So the loop-like model just shows the peak performance by operational intensity. So operational intensity. So if you see the unit of the operational intensity, so you can find that it's the flops divided by bytes. What does that mean? So flops represent the computation, and then byte represent the data. So operational intensity just represents the fractions of computation to size of data used for computation. Okay. And then actually our application will exhibit the various operational intensity levels. Then the loop-like model just represent the peak performance by this operational intensity, and then actually this slope, as I mentioned, this slope is determined by memory system. So hardware resources in the memory system, such as the memory bandwidth, and then this horizontal line of the loop-like model is determined by computation hardware resources. Okay. So if we observe this operational intensity, then we can say that this leftmost part of this operational intensity means that this is the memory intensive applications. So it's a memory intensive. And then we can say that this part of the application is the compute intensive application. Okay. So the process architecture, the performance of the compute intensive application is determined by computation resources. It's obvious, right? So it is determined by number of cores or some different type of cores, such as the tensor core in a GPU. But this part of application, so it's a the performance of memory intensive application is determined by the memory system resources, right? So, and this, okay. Then based on the characteristics of application, so operational intensity, so we can expect a big performance of the application using loop-right model. Okay, and then we can apply some different architectural technique on the GPU, and then using this different kind of architectural technique, then we can also improve the performance of the GPU. And then, as I explained, this slope of the loop-right model is determined by the performance of GPU memory systems. And then, it's a kind of architectural technique of memory coalescing. So with the memory coalescing, then the performance of this GPU can be improved. But this model just explains some different characteristics of GPU applications. So this operational intensity just explains the fractions of computation and data size. Irregular memory accesses cannot be represented using this operational intensity. Right? So think like this. We can just access the AI equal BI plus CI. And then also we can say that A Z B Z plus I plus blah 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 plus C I plus J plus K plus blah blah blah. So what is the difference? So in this example, this is a very simple array operation, but as you can see, this equation just handles the same amount of data. But what is different? How the indexes are generated for the array data. So the GPU application, we can say that this statement can generate the very regular memory access patterns. So I said regular memory access pattern, but it's the same add operation, but this array this array element is just accessed by different kind of index generation function. Okay, so which means that even though it's the same add operation, the regular operation may generate the irregular memory access patterns. What is the problem of the irregular memory access patterns? It is not coalesced in the WAP. So if the irregular memory access patterns are observed, then a single WAP may generate multiple memory accesses. And then, in this roof-line model, the performance of the GPU is determined by different coils level. So this slope does generate the 16 memory transactions per warp at 842. And when this the performance is improved if a warp generates a single memory transaction. But if a warp generates 16 memory transactions, then we can observe that GPU's peak performance is decreased. Okay. So with the memory balancing, then we can also improve the performance of the GPU. Also, this horizontal line is determined by computation core, the GPU. So if we use has a course, then we can also increase this computation capability. Also, if we use some special function unit, also we can improve the performance of the computation part. So with the loop-line model, then we can explain how the performance can be improved by some architectural solutions in the memory system or architectural solutions in the processor cores. Okay. Then, so another performance factor is the branch divergence. So this is some unique feature of the SIMT architecture. So SIMT architecture supports the diverged branch. So branch divergence is supported by SIMT. So what is the branch divergence? So when the branch is executed, then we can already know that the thread can be executed to this path, this execution path, and then another execution path used by branch instruction. Then in the SIMT architecture, of the GPU also supports the diverged branch. So which means that GPU also supports the branch instruction, and then based on the branch instruction, the execution path can be also divergent. Oh, it's very convenient. So which means that we can generate some very complex code using many branch instructions in GPU. Oh, it's very convenient. And what is the issue? Performance. What? So if GPU applications includes the many diverse branch instructions, I said diverse branch instructions, then we cannot get the peak performance of the GPU hardware, right? So I said the GPU use a warp is the group of thread, and then NVIDIA GPU. NVIDIA GPU single warp includes the 32 threads. Now, how can you support the diverse branch instruction? So why GPU groups the thread into a warp? Because inside the GPU hardware looks like SIMD architecture, and then we can increase the efficiency of the SIMD architecture if the multiple thread execute the same instructions. So which means that actually SIMD architecture, in the SIMD architecture, the multiple thread, not multiple thread, only one instruction, and there is the vector type data, the multiple elements, which includes the multiple elements. And then this instruction, for the multiple data, the same instructions are applied, and we can increase the efficiency of the SIMD architecture. So if a GPU hardware, the GPU applications work like a SIMD architecture, so like a SIMD, then we can increase the efficiency of GPU. So which means that, well, this is the one example of the divergent branch. So you can find the branch instruction here, and after this branch instruction, then the thread can be executed to this path. Also, thread can be executed to another path here. And then before this branch instruction, this thread execute the same instruction. So which means that for this instruction, a warp execute the same 32 instructions. Okay, so same instruction, same 32 instructions. So it's like the SIMD. So for this branch instruction, this warp generator, it's the same warp, a different instruction, or this warp execute the 32 same instructions. But you know, after this branch instruction, the execution path is diverse. So which means that among 32 threads, some thread may execute the instructions in this path, and then other threads may execute the instruction in different path. So for this instruction, or warp execute the 32 instructions. But among these 32 instructions, the execution path is diverse. So warp need to execute some instructions, but the number of instructions in this warp is less than 32. So for example, 16 threads can execute this path. Also, 16 threads can execute this path. So what's the problem? If a warp executes the 32 threads concurrently, then we can efficiently use the GPU's computer cores. Okay. Therefore, this warp can execute the 32 instructions concurrently. But after this branch instruction or this 16 thread execute the instructions in this path. So which means that a warp execute the instruction, but this warp just execute the 16 instructions. Okay, this part is empty because the execution path is divergent. So the GPU, color changed. So I don't know why the colors of the PDF are changing. So for this path, a warp just execute the part of thread. So for example, it's a 16 thread, and then this warp just execute the instructions in this path. But the number of thread, it becomes the 16. This part is empty. And then this is divergent branch. So the same warp need to also execute the different instructions in the different execution path. So not to execute this path, then a warp also execute the other thread. So in this case, this thread is empty. Okay. And in order to support the SIMD operation, the GPU has the active mask called, and then this active mask decides how many threads are executed in a single warp. Okay. So in this example, when the warp execute this instruction, the branch instruction, this warp execute all threads, the instructions in all threads. So active mask becomes 1, 1, 1, 1, 1, 1, 1, 1. But when a warp execute the PC instruction, then active mask becomes the 1111 0000 Okay. Then so GPU another support to diverse branch, GPU hardware is exploits the active mask, and then it's active mask, and GPU change the change the threads in a warp are executed or not under certain instruction. And what's the problem? When this warp instruction is executed, then simply the IPC instruction per cycle can be 32, just 32. Simply, but when this warp execute the instruction 0x0013, then IPC becomes the 16. The IPC is decreased. Then when the IPC is decreased, then GPU performance is also decreased. 16. So GPU supports the SIMT model, so SIMT programming model, so which means that GPU supports the diverse branch instructions. But when the diverse branch instructions are used in GPU applications, then the performance can be degraded. But we can find the branch instructions in the general purpose application frequently, So actually in the CPU applications, the frequency of the branch instruction is around the one branch instruction per 4 or 5 instructions. So which means that the frequency of the branch instruction is 4.5 instructions. So if we just fetch the 4 instructions or 5 instructions, then we can find at least one branch instruction. Okay? So this is the characteristics of the general purpose application. So recently, many general purpose applications are ported to GPU domains, and then actually another performance issue of this general purpose GPU is the branch divergence. Okay? So this is not another performance degradation issue of GPU architecture. Okay? So actually we can also we can use the GPU architecture simulator for our research. The most famous GPU architecture simulator is the GPU-GPU-C. So GPU-GPU-C is the cycle actuate simulator. So we can implement the GPU pipeline, or can implement the GPU memory systems using GPU-GPU-C. Okay. So this is the end of the GPU part. And actually, next semester I will cover the GPU architecture. Okay. Okay, so let's take a 10-minute break. I post the comment report after this class. We take the final exam on June 14 during the regular class time. Then this exam is the open book exam, so you can refer any slide deck, also any documents regarding this course. But you cannot use the electric devices during the exam, but you can use only the simple calculator. Okay, but you cannot use the smartphones, you cannot use the tablets or computers during the exam. Okay. So now also I will briefly introduce about the domain-specific architectures, and then because domain-specific architecture is very so recently the domain-specific architecture is the popular research topics of the computer architecture area, because so we are facing the end of the Moore's law. So I briefly explain about the domain-specific architecture. So this slide shows the Moore's law, and not Moore's law actually. So it's a comment that it's so I said the Moore's law is ending recently. Then so actually the Moore's law is the empirical law. It was the Gordon Moore. He is one of the founders of Intel, so a famous processor company. So then he just announced the Moore's law based on some observations. So this is the empirical law. So it's a kind of economical trend in the processor industry and the semiconductor technology. Okay, it's not the serious technology law, but it's not a kind of technology theory. Okay, it's a kind of a economical trend. Okay, but actually, it's like Moore's law is a very famous law in the computer architecture field or computer processor field. It is because based on the Moore's law, Intel set some target of the processor performance. Okay, and then Moore's law just expect some advances in the semiconductor technology, which means that the Moore's law defines the number of transistors in the same area, and then Moore's law just to say that says that the number of transistors doubles every 2 years. Okay, which means that we can utilize that is good semiconductor devices for improving the performance of CPUs. First, Moore's Furthermore also said that Moore's law can't continue forever. So we have another 10 to 20 years before we reach fundamental limit. So fundamental limit. So and then he said this announcement in 2005. So actually, we are facing the 20 years since the 2005. So the Moore's law is ending, so which means that it's very hard to use the very good transistors. So nowadays, the semiconductor technology is very critical for the economy of certain nations. Also, this semiconductor technology is also very critical for the some chip industry. Okay, also it's very critical for our nation's industry and economy. But so you know sometimes the news said that some kind of 3 nanometer technology, Samsung's 4 nanometer technology, or TSMC's 5 nanometer technology. So this means the width of the transistor channel, is the CMOS transistor channel. And then, so if we reduce this channel width, then we can manufacture the small transistor devices. And so it can generate the smaller small transistors. And the characteristics are also improved, such as the supply voltage and then the power consumption, the dynamic power consumption. So the speed of the transistor can be improved. So actually, Dennard scaling ended. So we cannot benefit from Dennard scaling, the scaling of the transistor. Which means that if we increase the number of transistors in the same area, then power consumption is increased. It's very critical actually, because the power is the very critical factors that determines the cost of the processor. Also, the power determines the manufacturing cost for CPUs. So power is increasing for a unit area. Okay, and then number of transistors. So because of this power constraint, because of and another scaling, so our process architecture is changed to the multi-core architecture. Okay, so with the multi-core architecture, we can improve the throughput of our processors, not latency. The performance of the single core processor is saturated recently, but with the multi-core architecture, then we can improve the performance throughput of our processors. And then this can be enabled by Moore's law actually. So number of transistors can be increased thanks to the advanced in semiconductor technology. But furthermore, we are reaching to a fundamental limit, so which means that the transistor scaling is facing the end, okay, end of the transistor scaling. Which means that it's very hard. So we may, so maybe some big companies such as TSMC or Samsung can develop those 2 nanometer or 1 nanometer technology, but it's very, very hard. Okay. So with the Moore's law, then we can also improve the process architectures, which means that these architectures like heap pipelines and then wide assembly, so branch prediction, executions. So actually, these architectural techniques require more hardware resources, and then more hardware resources can be enabled by Moore's law actually, which means that the more hardware resources require more transistors, but more transistors can be included in the same chip area. So with these architectural techniques, we can improve the performance, but we are facing the Moore's law. Also, this is the very popular very popular figure that explains why we require domain-specific architecture. So this figure just shows the breakdowns of the power consumption by processor operations. So if you see the required powers for executing a single with the instruction, then you can measure the required power like this. So this is the power required by ALU. So actually, not to execute an instruction, we require ALU. Actually, the ALU is the main part of executing instructions, right? So data is moved to the ALU, and then ALU performs the required operations for instruction, and then ALU generates the result from an instruction. So ALU is the main part of executing instructions. But in order to execute a single instruction, a processor requires this amount of power. Why? So we learned about the out of the process architecture. In order to execute an instruction, then an instruction needs to be fetched from the instruction memory, and then this instruction is included in the instruction fetch queue, and then instructions are decoded and then dispatched to the issue queues. And at the same time, when an instruction is dispatched, this instruction is also registered in ROB, view the buffer. Also, we need to control the register LS table. And when the execution is completed, and the result is moved to the physical register file. We update this register LS table. We also update the view the buffer. Also, we apply the prediction techniques such as the branch prediction, the memory disambiguation, the return stack, return address stack. So many prediction technologies, many predictions are applied to our processor. So in order to execute a single instruction, many operations. So many architectural techniques are required. And then this power override represents the required power consumption, required power consumed by these components that is required that are required for executing instructions. Okay, so overall the executing instruction is much larger than the power required by EEU, even though this is the main function. And then if the load store instruction is required, then we need to also subscribe the cache. So memory, actually the memory also consumes the actual power. Because the memory size is very large compared to the execution units. Also, actually, the size matters for power consumption recently. So, for the older generation processors, the dynamic power dominance, the total power consumption, but recently, the static power dominance, the power consumption. So which means that if the memory component is actually cold, it's a cold device, cool device. So which means that the memory cells in the memory components are rarely touched by instructions, rarely touched by the operations. But memory components occupy the large area of processing. Okay. And then the transistors are working, just the power is turned on for the transistor. Now the transistor consumes the much of power because of static power consumption. The problem is that the size of the transistor is reduced. So which means that the performance on and off function of this transistor does not working well. So even though the transistor is off, charges pass through the transistor channel. That's why static power is increased recently, which means that, so think like this, the memory components occupy the large area, and then actually this memory is turned on, which means the supply voltage is provided to this memory component. So based on the area, occupied area, this memory will consume actual power. So this is another problem. So when memory instructions are executed, we also require the additional power for the memory components. So even though AAU is the main function or main processing the processor cores, but AAU just consumes the small amount of power. But in order to execute a general purpose instruction, then lots of power is consumed. And this is the critical problem. So I believe some of you already knows about some performance metrics such as the per watt. Okay. So why this metric is important recently? So the watt power, the electric power is the running cost in the data center or server systems. And actually, these data centers want to run the applications or want to gain high performance using the small amount of electric power. Okay, so that's why the top per watt is the important performance metric we sent. So then, how can we increase? How can we increase this performance per watt performance metric? Oh, you can just see this observation. So you want to execute a general purpose instruction. This is the required power overhead. And then if we can reduce this overhead, power overhead by instruction, then we can increase the performance per watt. Okay. And then another good thing is that if we just focus on the single point, floating point execution, then the required power is reduced to the 15 to 20 picojoule. So if we just focus on the 30-bit fixed point addition, then just 7 picojoule, and then 8-bit 0.2 or 0.5 picojoule. So, which means that if we just reduce the resolution of our data, then we can also reduce the required power. Okay, so that's why we are focusing on the domain-specific architecture. Actually, have you heard about the ASIC? So it's actually ASIC means just a custom chip. Okay, so if we can build the ASIC, then ASIC will exhibit the most efficient power performance power. So because ASIC is the custom chip. But with the ASIC, we cannot execute the instructions. So what is the main feature of the processor? So main feature of the processor is with the processor we can execute instructions, and then which means that we can run general purpose applications. But with the ASIC, it's a custom chip just runs some fixed operation. So performs the fixed operation, and then we can control the very small part of this ASIC custom chip, but power efficiency is much higher than the general purpose processor. So domain specific, this is the general purpose processor. Then this is the ASIC. So general purpose processor supports the programmability. Then, but the power efficiency is very low. The ASIC just supports the fixed operation, but power efficiency is very high. So because of the programmability, we are using general purpose processors such as the CPU, like ARM processor or GPU. GPUs can also execute some general purpose instructions or general purpose application. But power matters. So we are focusing on some intermediate region between general purpose processor and ASIC. Then this is the domain-specific architecture. So using the domain-specific architecture, we just focus on some domain-specific application. Okay, so which means, so for example, so Google TPU, the tensor processor unit, can just accelerate the matrix operations. Okay, but we can also give we can also give some instructions or define the instructions to TPU. So which means that we can run some specific applications using TPU. Okay. So, but this domain specific the process architecture of the domain specific architecture actually very similar to AC. Okay. So it's totally different from the general purpose processor we run in this course, like the out-of-order processor. Then it's also different from some CMD architecture or some different kind of architecture, such as the vector processors. So it's different. So if we just see the architecture, process architecture of the domain specific architecture, then it's similar to the hardware architectures of the AC. Okay, but we can domain specific architecture also supports the programmability defined by instruction set architecture, but domain specific architecture will just focus on a specific domain, specific operations in a certain domain of applications, and then just accelerate them on certain operations. Okay. So when we focus on the domain specific architecture, then we need to focus on also the data movement. The required data should be moved to the dedicated memory such as the device memory of the domain specific processor. Also, this data should be moved to the scratchpad memory or internal buffers in the DSA. So data movement is also very important because recently the cost of for the data movement is much higher than the cost for executing some data. So which means that the cost for data movement is higher than the cost of execution. Okay. And then, so we learned about the loop line model of the CPU or the general purpose processor, but we can also apply this loop line model to the domain specific architecture. So for example, we can focus on the TPU. So TPU is designed for executing matrix of multiplication, and then in order to increase the computation peak performance for the compute intensive application, then we need to invest the more hardware resources like the processing engines or processing units. So we also invest some more arithmetic units or more hardware, also bigger memories like the bigger internal memories or bigger scratch pad memory. And then terrorism. The terrorism is always good. Okay? So we need to always exploit the terrorism, and then it's also very important. So the domain specific architecture should be supported by domain specific programming languages. Okay, so recently we can easily use the GPU. Actually, we can easily run neural network applications using these neural network frameworks such as the PyTorch and TensorFlow. Okay. But so in order to, and then as I mentioned, in order to use the GPU hardware efficiently, but we need to know some specific architecture of the GPU. Also, we need to learn how to use those specific hardware resources or memory systems of GPU. But the framework, this is the framework. The framework hides the detailed part of the GPU programming or GPU architecture. We just use set the size of the matrix, so we just connect some different, you apply the build the different networks between the input and output object. So this is kind of abstraction. So actually the framework supports the generate those GPU code based on our design. But so in order to use the domain-specific architecture, the domain-specific language should be developed. So for example, the Tensor TPU, Google TPU also has some instruction set architectures, the instruction set, and then this actually in order to use the TPU, then our program needs to be compiled to the instructions which are used by TPU. Okay, so and then which means that we also need some framework that supports the TPU, and then this framework needs to compile our normal application, which can be executed by TPU architecture. Okay. Domain-specific programming language is also very critical for the DSA. So this table shows some example of the domain-specific architectures. So TPU is the most famous DSA. Okay, so it is used. It is deployed in the Google Data Center, and also it's a kind of some old information. So you can find the dedicated memory, and then also you can find the number of processing units here. Okay, so you can find the size of the memory here, and then the number of processing units, and then how the parallelisms are exploited here. Then smaller data size is a kind of their resolution of the data. So as I mentioned, as I showed in this figure, so actually if we reduce the resolution of our data, then we can also reduce the required power for operation. So the reason is that it reduces the TPU, and TPU supports the 8-bit or 16-bit integer data. So it says 8-bit or actually this is the 8-bit or 16-bit fixed point data. So usually let's consider the integer. What's the size of the typical integer type data? It's over. It's a 32-bit. So compared to the typical integer type data, the data resolution used by TPU is also data resolution is lower than the typical integer type data. Okay, we can use the TensorFlow for using this TPU. And then Catapult is developed by Microsoft, it's a software companies. The TPU was developed by Google, it's a software company. And then Crest is developed by Intel, and it's also Pixel Visual Core is developed by Google. Okay, so you can find some different specification for some domain-specific architectures. Okay. And then actually this slide explains some specific features of the domain-specific applications. You know, the TPUs are actually used for deep neural networks or convolutional neural networks. So actually, in order to design the domain-specific architecture, then we first analyze the characteristics of application in specific domains. Right? Think about the Amdahl's law. Why Amdahl's law is important? So actually the performance is determined by a part that cannot be improved. Okay, that's what Amdahl's law says to us. The performance is determined by a part that is not improved. Okay. Then how about the domain-specific architecture? With the domain-specific architecture, then we can improve a certain operations. So for example, with the TPU is not just matrix multiplication unit. So TPU is just includes the matrix multiplication unit. Okay, which means that TPU can just accelerate the MM operations, and that's it. So why do we need to accelerate MM operations? Because neural networks includes lots of matrix operations, and then in a CPU, matrix operation is not efficient. Then also because these neural networks handles the large amount of data and the large amount of matrix multiplication, this operation is not good for the CPU architecture. Also, then we can use the GPU, and then GPU architecture is better than CPU for the parallel applications, but it's not also good for the matrix multiplication. So actually the GPU also receives the array data. Okay, but each thread of the GPU just sends some element. So in order to implement the matrix multiplication, GPUs also just read some column and row from a matrix array, then also applies the map operation, multiply and accumulation operation, like add operation actually, for each vector multiplication. So in order to perform the matrix multiplication, GPU needs to execute the multiple instructions that access multiple array vector data. So GPU has the more efficient hardware than CPU for matrix multiplication, but GPU is also not efficient. So okay. So recently the GPU has tensor cores. Actually, the tensor cores just support the matrix multiplication, matrix instructions. Okay. So, but why? Why matrix multiplication? Some applications, I said some applications like neural network applications handle large amount of matrix multiplications. But why neural networks? GPU is the general purpose GPU. So we use GPU for the general purpose applications. But TPU is only good for the matrix multiplication. It's demanded by neural network applications. And why neural network applications? Because neural network applications are popular recently. And then in order to run the popular application, in order to accelerate the popular applications, we can apply the domain-specific architecture based on the Amdahl's law. Because this application is very popular, then the fractions of the fractions for the workload, the amount of workload for this type of application is increasing today, which means that P is the let us assume that S is the some fraction of some other application, and then P is the fraction of some is neural network domain applications. And this P is increasing recently. So if we improve the performance of this fraction of P with the domain-specific architecture, then we can improve the performance. Okay? So also in the domain-specific architecture, I mentioned the matrix multiplication. Why matrix multiplication? Matrix multiplications are frequently used, and then these neural network applications require lots of matrix multiplication, which means if we can accelerate the operation inside of neural network applications, then we can improve the performance dramatically based on the Amdahl's law. So in order to, so that's why we need to analyze the characteristics of specific domain applications before diving into the domain-specific architectures. Okay. So actually, this slide explains the specific feature of the neural network applications, but I will skip this part. So this slide just explains some operations, the algorithm of the popular neural networks or some neural networks applications. Okay. So summary. So if you are interested, you can read this slide summary. What these applications, so like the CMNs or DNNs, RNNs, scans, just require this kind of computation kernel. Matrix beta multiplication, matrix stencil, the loop, sigmoid. So this is the activation functions. So if these computation kernels can be accelerated, because these computation kernels are frequently used in these domain-specific applications like the neural networks, then we can build the hardware that can execute these type of operations. It's kind of very similar to the ASIC. Because in order to execute these computation kernels, then with the general purpose processors, we just write the code that execute these computation kernels, and then this code is compiled into the instructions that are supported by general purpose processors. That's what we have done for these computation kernels. But with the ASIC, then we can build the ASIC, the custom chip that supports these operations, these computations. But the disadvantages of ASIC chip is that we cannot use the instructions. We cannot. So ASIC chip has a lack of programmability. So it's not good for the programmability. So because these computation kernels are frequently used, and we can build some domain-specific architectures that can accelerate the performance of these functions. Okay, Google TPU, so actually when the TPU was firstly announced, it was very sensational because TPU was developed by Google, very famous and big company, and then actually TPUs are deployed in the Google data center, and then TPUs are used for the inference or training of the deep neural networks or convolutional neural networks in the Google data center. So TPU is the very famous domain-specific architecture, but it's called the Google's DNA ASIC. So sometimes Google engineers call TPU as the ASIC chip because this structure of the architecture of this TPU is very similar to the architecture of ASIC, the hardware architecture of ASIC. And then, as I mentioned, this TPU just includes the matrix multiplied unit. Okay, 256 by 256. Then also scratch pad memory. It's a kind of a feature of the ASIC also. And then TPU is the coprocessor. So in order to run the neural network applications, then these neural network applications should be launched on the operating system, launched by the operating system, and then also managed on the Google servers. So actually, so TPU is the coprocessor. Okay? GPU is also coprocessor. So we cannot run operating system using GPUs. So TPUs, like the GPU, TPUs are also connected via PCIe bus. Okay. Then this is the architecture of the TPU, and then as you can see, this architecture is different from the architecture of general purpose processors. Okay. So TPU has this is the PCI interface. So as I mentioned, the TPU is connected to hosted via PCI bus, and then so which means that the TPU has the host interface. So it just the host interface just manages the data transfers between host systems, and then TPU has its device memory. So this is the first version of the TPU. So this TPU uses the DDR3 DRAM. Somewhat old. So, and then it's same to actually GPU. If you use the GPU chip, then you can find the many device memories around this large GPU chips. Actually, you can see only the you can see only what's that? So big fan on the GPU board, but actually under the graphic fans, and you can find the large GPU chip and then the many device memories around the GPU chip. And then actually it's the same to the TPU. The black box is growing. So if you have dedicated the internal memory, like the memory, and then this is the main part of the TPU. So as you can see, TPU has the matrix multiplication unit. Then this matrix multiplication unit receives data, and that performs the matrix multiplication instruction. Okay, and then the result is also stored to the device memory, and then these results are transferred to the host system. So that's how the TPU works. And then actually Google doesn't reveal the instruction sets used by TPU, but they just revealed some kinds of instructions, just the 5 instructions on the TPU paper. Actually very simple. So if you see some instruction set supported by TPU, you can find, oh, this is the instruction that handles the data transfers between the host and TPU. And that's all like the read host memory and the read wait. So this read wait is also some kind of instruction that read the wait data from the memory. And then matrix multiply or convolution. So this instruction performs the matrix multiplication and then convolution operation using TPU. But this is kind of instruction. Okay, this instruction. So which means that this instruction, the matrix is read from the memory. No, the matrix is stored in the internal memory, like scratch pad memory. And then this matrix data is read by the TPU hardware. Then the TPU hardware automatically performs the matrix multiplication. And the activate instruction just performs the activate functions regarded by GMN or DMN, then write to host memory. So if you see, so actually the detailed instructions are not revealed because it's the commodity processors. But as you can see, so TPU just supports the very small number of instructions. And then, if you see actually these three instructions just handle the data transfers between TPU and host systems. And then TPU just supports the two instructions, matrix multiplication and activate instruction. It's very simple. If we see some instructions executed by TPU, then we can find that, oh, it's very simple. And then the number of instructions supported by TPU is very small, right? Because of this. So if we support the domain specific architecture supports the many different instructions, and then the power override by executing these instructions will be very high. But TPU supports the small number of instructions, and then so TPU architecture is simpler compared to the general purpose CPUs or general purpose GPU. Okay. And then this figure is also revealed by Google. So Google just reported some area of GPU chip using some various components. So as you can see, the size of the internal memory occupies the 29% of the chip. The internal memory just unified buffer, the internal memory just occupies the 29%, and then matrix MN unit. So execution unit just occupies the 24% of the entire TPU chip. So it's over 50%. So you see the so guidelines for DSA, then you can find the bigger memory and then the large amount of arithmetic units. So TPU is also is the same. So also you can find some additional hardware components. But, the hardware resources occupied by this component is very low. And then, so this figure shows how TPU performs the matrix of multiplication. So this architecture is known as the systolic array. Actually, using the systolic array, the data is moved to the target processing unit, and then the data flows like destruction and destruction. So the result is flows the destruction and the data flows the destruction. And by doing this, the weights data is weights data are multiplied by input data by GPU. And so these results are also presented by Google. So you can find this result on the Google TPU paper. Actually Google announced that their performance per power of the TPU is higher than the CPU or GPU. Okay? So as I mentioned, performance per power is very important performance battery of the data center or some modern architectures. So Google presented that their TPU's performance per watt is higher than the traditional GPU or CPU. I attended ISCA 2017, right? So actually Google announced the TPU at ISCA 2017. So actually the TPU paper was the first paper of so it's the first presented paper at ISCA. So the Google when Google presented this TPU paper, so Google just compares this performance of the TPU with the GPU, NVIDIA GPU actually. So and then the NVIDIA engineers argued that they just in this paper that Google just used the old generation of the GPU. They argued during the conference, ISCA conference. Actually, it was very interesting. So, okay, so actually there are many kinds of domain-specific architectures like Microsoft Catapult. Actually, the Catapult implement the PG and then the dedicated DRAM. So if you see that architecture of this Catapult, then you can find Catapult is also designed for the matrix multiplication. So that's why the processing engines are organized in the 2D dimension like this. And then each processing engines are connected networks. Okay. And then so we can find the cluster. So we can also use the FPGA accelerators. So actually this time, so I will not explain the detailed architecture of these domain-specific architectures. But I want you to understand why domain-specific architectures are required recently, and why many researchers focus on the domain-specific architectures. Okay. Okay, so and if you are interested, you can find some papers that present some detailed architecture properties, TPU and Catapult and Crest. Okay. So I stop here. Any questions? Okay, thank you for your attention. And the next class is the class. Actually, I plan to cover the memory systems of the memory systems, but we don't have enough time. But in the last class, I will briefly cover the memory systems and some memory systems of the multi-core or some advanced level of the memory systems. Okay. Okay, thank you, and see you in the next class.